This is a quick demonstration of how to use Vivado to do a simple simulation. I am not a digital designer, and I find Vivado quite overwhelming in the sense that there's such a lot of things built into its little windowing environment. And it can be intimidating even for, smart folks who want to use it. So let me give a very simple example of at least getting it to simulate something. So here's this Vivado. This is 2017.2, the latest one at the time of recording this. And we'll create a new project. The new project, I'm going to call it For Steve, because I have in mind a particular guy that we work with in the UK. So here, For Steve, and we'll put it in that place, play, create project subdirectory. I do not wish to specify sources at this time because I don't have any. Next. And then the part, it doesn't matter what part we select, I'm just going to pick that one at random. That one will do. Next. And finish. So now Vivado will create an empty project for us, and we can change any of these things at any time. So I'm going to say now to add some sources to it. Add or create design sources. So the first thing we're going to do is create a file, a Verilog file called For Steve. Well, yeah, okay, For Steve, because I think that's what I called the project, right? Local to the project, and add another one, create another new file called For Steve Test. You'll see why we need that in a minute. For Steve Test. Did I spell those correctly? Yes, I did. And then add those files. Oh no, sorry, cancel that. And then finish. Right, now the first file, look, it's trying to help us out. It's giving us an opportunity to specify ports and things. Now the common methodology that we use is we always have a clock, an input. We always have a clock enable signal, which tells us the clock when to run. And we always have a reset. These are the common controls, and they're all inputs and they're not a bus. And then in this example, I'm going to make a counter. So I'm just going to have a thing called count. And this one is going to be an output, and it's a bus, and we'll have it go from 15, I think that'll work, to 0. So I think that should do it. And then for this one, there are going to be no ports on this one. You'll see why. We should be good. Some files have not been changed. Are you sure you want to? Yes. Fair enough. Right. So now we're going to edit these files and add some stuff to them. So in this For Steve file here, we're going to use the internal editor, which Xilinx provide. And it's done an outline for us, look, where it's used the particular syntax of embedding the descriptions within the argument list. Not my favorite way of doing it, to be frank, but let's just go with it. Now that count is also, as well as being an output, a register. So I'm going to tell it that that is in addition to all that other stuff. Count is a register. And then we're going to follow the standard methodology, which is always at the positive edge of the clock, we're going to do things. If reset is true, what we always do is initialize stuff. There's only one thing we need to initialize here. Count goes to 0. End that stuff there. Now, else, if the clock is enabled, so we're not reset now, so don't force it to be 0, but if the clock is enabled, begin, count is assigned to count plus 1. It's easy as that. End, and that's it. So all this module does is, every time clock comes along, if we're not in the reset state, if the clock is enabled, count increments, and count will ultimately overflow when it reaches, a 16-bit quantity there. So that'll do. Now, that's what we need to define our little counter logic, but to test it, we need to write a test file. So this test file here, it's got no arguments, which I think God intended that be on the same line like that. But we're going to have to set up within here registers to allow us to set and clear those registers and stimulate our circuit. So there's a register called clock, enable, and reset. Those are the three usual suspects that we'll need. We'll also need a wire to look what's going on. And this time I'll call it Y for no good reason. I'm just going to hook up Y to it. Now, in the test bench, we call for this initial statement. Initially, I think it's initial or is it initially? I can never remember. I'm going to just have a quick peek at a known good guy over here. This, by the way, is Emacs. This is what I normally use for writing Verilog. But we're doing it in the other environment now. And as you can see, it's initial. Look, it's initial, not initially. So go back to this guy, initial. And when we start, begin, what do we want to do? Clock is 0. Clock enable, I'll make him 1. And reset, I'll make him 1 as well. So when we first come to life, clock's enabled, but we'll reset. And then, after a certain time, after 100 nanoseconds. After 100 nanoseconds, we'll take the reset high again. Notice I'm using equals rather than that assignment because that works in initial, so I just use it. And then we'll hang about for a long time. We'll hang about for a million time intervals. The million time intervals being nanoseconds, and the nice thing about Verilog is you can put that underscore in there, which helps you count the zeros. And then I think we have to then end that. Oh, I'm calling, there's this statement, $finish. That statement causes the simulation to stop. I don't know whether I need it or not. Let me put it in for now. Finish, did I spell it right? No, there we go. That's the system task and it'll cause it to stop. And then that's the end of that initial begin business. Now, we want certain things to happen always after a delay of 80 nanoseconds. 80 nanoseconds, I chose that because it's less than the reset time. So the reset and the clock are not coming at the same time. I just pulled that out of the air. Clock is assigned to, not the clock. Right? And I think that's pretty much everything we need here. The reset will go, the reset will go away. Whoa. The reset will go away at 100 nanoseconds. The clock was enabled over time. The clock's going to bang along about 12 megs. So all we need now to do is instantiate that module. Well, the module was called for Steve, if I'm not mistaken. And we're going to call it the instance U1. I know it requires, if we remember, clock enable, reset, and then I'm going to give it that wire. And I believe that should do it. So let's save that and see if the tool is happy. Right, so we have a test circuit. So down here, look how you got to admire the little clever things. The tool has figured out that this simulation test bench must be for Steve test. I'm sure it's done it because it's found there's no arguments in this list here. So we can pretty much run the simulation now. Run sim. I almost always get it wrong first time. Never mind. Right. So it's now creating that code. Oh, I got it right. Holy cow! All right. So, and this is the output. Now, one very confusing thing, or at least the thing I find confusing, is some of these simulators, they don't run to the end. I'll just let this guy run to the end. Bang. Now it's sitting at that $finish statement. So we ran for 1 million nanoseconds, or 1 millisecond. Let's go back to that guy and we should see it. I guess we have to zoom out or something, do we? Yeah, there we go, look. So there, Steve, we got it. You can see now that we created something and the something worked. There's a clock banging along. Clock enables high all the time. Reset went away near the beginning, somewhere over here. It was undefined until that clock edge came when reset was true, and then the thing worked. So what we've just seen is that a quick way to write some code which verifies that it's instantiable or synthesizable, because the Verilog tool turns it into Verilog gates and then simulates the gates. So that should be it. I hope it helps.